Hello there and welcome to the Sleepy Facts channel. I'm so glad you found your way here. Maybe you had a long day filled with earthly concerns, or perhaps you're the kind of person who finds comfort in cosmic perspectives rather than counting sheep. Either way, tonight's gentle journey through 99 sleepy facts about our home galaxy is crafted just for you. You've got nothing to do but rest. Let your mind relax, your breathing slow, and your body grow light as if you're floating weightlessly through the starlit corridors of space itself. Tonight, we're not simply learning facts, we're drifting through the quiet mysteries of the Milky Way, one gentle revelation at a time. Our galaxy holds secrets that span billions of years, from ancient collisions that shaped its spiral arms to the invisible forces that keep it spinning in the cosmic dark. We'll explore rogue stars fleeing into intergalactic night, stellar nurseries where new suns are born in silence, and the hidden scaffolding of dark matter that holds everything together like an invisible embrace. Some of what you hear tonight may surprise you, or at the very least, offer your mind a peaceful place to wander as sleep begins to find you. And just before we begin our cosmic count, if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps other sleepy souls find their way here too, one gentle fact at a time. Now, let's begin our journey through 99 sleepy facts about the Milky Way. Fact number 1. The Milky Way is a barred spiral galaxy. Our home galaxy belongs to a family called barred spirals, distinguished by an elongated bar of stars crossing through its center. This bar, invisible to us from our position within the disk, rotates slowly like a cosmic stirring spoon, shaping the flow of gas and stars around it. From a great distance, the Milky Way would appear as a graceful spiral with arms curving outward from this central bridge of light. Fact number 2. It contains over 100 billion stars. Between 100 and 400 billion stars call the Milky Way home, though the exact number drifts in uncertainty like morning mist. Each star is a sun in its own right, many hosting their own families of worlds. The vastness of this stellar population means that even if we could count one star every second, it would take over 3,000 years just to reach 100 billion. We live in a city of suns too large for human comprehension. Fact number 3. The galaxy is 13.6 billion years old. Our galaxy formed when the universe was still young and wild, roughly 13.6 billion years ago. It has witnessed the birth and death of countless generations of stars, the slow accumulation of heavy elements, and the gradual settling of matter into the elegant spiral we know today. In galactic time, even the oldest human civilizations are but the briefest flicker of an eyelash. Fact number 4. We orbit the galactic center at 828,000 kilometers per hour. Even as you rest peacefully, you are racing through space at nearly 230 kilometers every second as part of the solar system's grand orbit around the Milky Way's heart. This tremendous speed feels like stillness, because everything around us moves together in the same cosmic dance. We are passengers on a gravitational carousel that never stops turning, spinning through the galaxy in quiet synchrony. Fact number 5. A galactic year. The time it takes our solar system to complete one full orbit around the galaxy's center is called a galactic year. In the 4.6 billion years since Earth formed, our planet has made only about 20 complete journeys around this vast wheel. The last time we were in this position in our galactic orbit, the supercontinent Pangaea was just beginning to break apart, and dinosaurs had not yet appeared. Fact number 6. The Milky Way is on a collision course with Andromeda. In approximately 4.5 billion years, our galaxy will merge with its nearest large neighbor, the Andromeda Galaxy. This cosmic collision will be a slow, elegant dance rather than a violent crash, as the spaces between stars are so vast that direct stellar impacts will be rare. The two spiral galaxies will stretch and distort each other with their gravity, eventually forming a single, larger elliptical galaxy that astronomers have already nicknamed Milkomeda. Fact number 7. Most of the galaxy's mass is invisible dark matter. Though we see the Milky Way as a luminous spiral of stars, the majority of its mass lies hidden in an enormous halo of dark matter that surrounds and permeates the visible structure. This mysterious substance does not emit, absorb, or reflect light, revealing itself only through its gravitational effects. Without dark matter's invisible embrace, the galaxy would fly apart, its stars scattered into the cosmic void like seeds on a stellar wind. Fact number 8. The galactic center harbors a supermassive black hole. At the very heart of the Milky Way lies Sagittarius A star, a supermassive black hole containing more than 4 million times the mass of our Sun. Though invisible itself, this cosmic giant reveals its presence through the frantic orbits of nearby stars, which race around it at speeds approaching 7,000 kilometers per second. It sleeps quietly now, but long ago it may have blazed like a quasar, illuminating the entire galaxy from within. Fact number 9. We live in a minor spiral arm called the Orion Spur. Our solar system doesn't reside in one of the Milky Way's grand spiral arms, but rather in a smaller structure called the Orion Spur or local arm. This relatively quiet stellar neighborhood sits between the larger Sagittarius and Perseus arms, like a peaceful side street between busy galactic highways. Our location in this calm region may have provided the stability necessary for complex life to evolve on Earth. Fact number 10. The galaxy is warped like a bent record. The Milky Way's disk is not perfectly flat but gently warped, curving upward on one side and downward on the other like a slowly undulating wave. This subtle distortion becomes more pronounced toward the galaxy's outer edges and may be caused by gravitational interactions with satellite galaxies or the uneven distribution of dark matter. Even galaxies, it seems, are not immune to the gentle reshaping forces of cosmic time. Fact number 11. Stellar streams trace the paths of destroyed galaxies. Wrapped around our galaxy like ghostly ribbons are stellar streams, long trails of stars torn from smaller galaxies that wandered too close to the Milky Way's gravitational embrace. These delicate structures, visible only through careful astronomical surveys, tell the story of cosmic cannibalism played out over billions of years. Each stream is a memorial to a small galaxy that once shone independently in the darkness of space. Fact number 12. The galaxy recycles its material across cosmic time. Stars are not permanent fixtures but temporary gatherings of cosmic material that eventually return their substance to the galaxy's vast reservoir. When massive stars explode as supernovas or smaller stars shed their outer layers as planetary nebulae, they enrich the interstellar medium with heavy elements forged in their cores. This enriched material eventually condenses into new stars, planets, and perhaps even life, creating an endless cycle of cosmic renewal. Fact number 13. Ancient stars in the halo predate the galaxy's disk. In the spherical halo surrounding our galaxy drift ancient stars that formed before the Milky Way's familiar disk structure had fully assembled. These stellar elders, poor in heavy elements and following highly elliptical orbits, are fossils from a time when our galaxy was still gathering itself from the primordial cosmic web. They move like slow, solitary wanderers through the galactic suburbs, carrying memories of a wilder, younger universe. Fact number 14. Hypervelocity stars escape the galaxy entirely. Occasionally, stars are accelerated to such tremendous speeds that they break free from the Milky Way's gravitational bonds and flee into intergalactic space. These hypervelocity stars, traveling at over 1,000 kilometers per second, are usually created when binary star systems venture too close to the central black hole, with one star falling in and the other being flung outward like a stone from a cosmic slingshot. They become lonely wanderers in the vast darkness between galaxies. Fact number 15. The galaxy contains over 150 globular clusters. Orbiting in the Milky Way's halo like ancient satellites are more than 150 globular clusters, dense, spherical collections of hundreds of thousands of old stars. These stellar cities are among the oldest objects in the galaxy, some containing stars more than 12 billion years old. They serve as time capsules, preserving the conditions and composition of the early universe in their tightly bound stellar populations. Fact number 16. Gas clouds larger than solar systems drift between the stars. The space between stars is not empty but filled with vast clouds of gas and dust, some spanning hundreds of light years across. These molecular clouds, cold and dark, are the nurseries where new stars are born. Within their shadowy depths, gravity slowly gathers material into dense knots that eventually collapse and ignite as newborn suns, continuing the galaxy's cycle of stellar birth and renewal. Fact number 17. The Milky Way's magnetic field threads through its entire structure. Though invisible to our eyes, Our galaxy is permeated by a vast magnetic field that influences the motion of charged particles and helps shape the flow of gas and cosmic rays. This galactic magnetic field, thousands of times weaker than Earth's but extending across hundreds of thousands of light years, plays a crucial role in star formation and the galaxy's overall structure. It is the galaxy's invisible nervous system, connecting distant regions through magnetic threads. Fact number 18. We can see only about 0.00003% of the galaxy's stars with naked eyes. Under the darkest skies, far from city lights, the human eye can distinguish perhaps 6/60 or those individual stars across the entire celestial sphere. This represents an infinitesimally small fraction of the Milky Way's stellar population, like seeing a few scattered lights from a city containing 100 million buildings. The vast majority of our galaxy's stars remain forever invisible to unaided human sight, hidden by distance, dust, or simple faintness. Fact number 19. The galaxy has eaten dozens of smaller galaxies. The Milky Way has grown over billions of years not just through star formation, but by gravitationally capturing and consuming smaller companion galaxies. Evidence of these ancient meals remains scattered throughout the galactic halo in the form of stellar streams and unusual star populations. Our galaxy is a composite structure built from the accumulated remains of many smaller systems that fell into its gravitational web over cosmic time. Fact number 20. Sagittarius dwarf galaxy is being torn apart right now. Currently undergoing destruction before our astronomical eyes is the Sagittarius dwarf elliptical galaxy, a small companion that is slowly being shredded by the Milky Way's tidal forces. As it orbits our galaxy, streams of its stars are being pulled away and scattered across the sky, forming long trails that wrap around the Milky Way like cosmic ribbons. This ongoing galactic cannibalism demonstrates that our galaxy continues to grow and evolve even today. Fact number 21. The Sun has completed fewer than 25 galactic orbits. In its 4.6 billion year lifetime, our Sun has made only about 25 complete journeys around the galactic center. Each orbit represents a vast epoch in cosmic and terrestrial history. Entire geological eras pass between galactic years. The Sun is still relatively young on this galactic timescale, having experienced less than a quarter century of galactic seasons since its birth from an ancient stellar nursery. Fact number 22. Dark matter outweighs normal matter 5 to 1 in our galaxy. For every kilogram of ordinary matter, stars, planets, gas, and dust that we can see in the Milky Way, approximately 5 kilograms of dark matter lurk invisibly in the galaxy's extended halo. This mysterious substance interacts gravitationally, but remains otherwise undetectable, forming an invisible skeleton that gives our galaxy its structure and stability. We live inside a vast cathedral of dark matter, whose architecture remains largely hidden from our senses. Fact number 23. The Milky Way is part of the Local Group. Our galaxy belongs to a small cluster called the Local Group, which contains more than 80 galaxies spread across about 10 million light-years of space. The Milky Way and Andromeda are the largest members, each accompanied by numerous smaller satellite galaxies. This gravitationally bound family of galaxies drifts together through the expanding universe, a small island of cosmic structure in the vast ocean of space. Fact number 24. Stellar formation peaked billions of years ago. The Milky Way was much more active in its youth, forming stars at a rate several times higher than today. The galaxy star formation peaked around 10 billion years ago and has been gradually declining ever since as the supply of pristine gas has been consumed or heated. We live in a quieter, more mature phase of galactic evolution, when star birth proceeds at a gentler, more sustainable pace. Fact number 25. The galaxy contains ancient metal-poor stars. Scattered throughout the galactic halo are extremely old stars that contain almost no elements heavier than hydrogen and helium. These metal-poor relics formed in the early universe before successive generations of supernovae had enriched the cosmos with heavy elements. They are living fossils that preserve the chemical conditions of a time when the universe was still young and the galaxy was just beginning to take shape. Fact number 26. Cosmic rays constantly pass through everything. Every second, high-energy particles called cosmic rays, accelerated by distant supernova and other violent cosmic events, stream through your body and everything around you. These energetic messengers carry information about conditions throughout the Milky Way, having traveled for millions of years through interstellar space before reaching Earth. They are the galaxy's whispered news, delivered in a language of invisible particles. Fact number 27. The galactic plane appears as the Milky Way in our sky, the band of light that stretches across Earth's night sky, which we call the Milky Way, is actually our edge on view through the galaxy's disk. When we look along the plane of the galaxy, we see the combined light of billions of distant stars, creating the impression of a luminous river flowing across the darkness. This view from within gives us only a flattened perspective of our three-dimensional cosmic home. Fact number 28. Giant bubbles of hot gas extend from the galactic center, stretching tens of thousands of light years above and below the Milky Way's center are enormous structures called the Fermi bubbles, vast lobes of high-energy gas that glow in gamma rays. These ghostly formations may be the remnants of a period of intense activity from the central black hole millions of years ago, when it may have shone like a brilliant quasar. They are invisible to our eyes, but represent some of the largest structures in our galaxy. Fact number 29. The galaxy rotates differentially like a whirlpool. Unlike a solid wheel, the Milky Way rotates differentially, with its inner regions spinning faster than its outer edges. This creates a shearing motion that helps maintain the spiral arm pattern as density waves propagate through the galactic disk. Stars drift in and out of these spiral arms over millions of years, like cars moving through traffic patterns on a cosmic highway. Fact number 30. Dust grains in space are smaller than smoke particles. The interstellar dust that obscures distant starlight and gives nebulae their dark silhouettes consists of particles typically smaller than those in cigarette smoke. These microscopic grains, composed mainly of carbon and silicate minerals, play crucial roles in stellar birth by helping gas clouds cool and collapse. Despite their tiny size, they collectively dim starlight and redden its color, creating the dark lanes visible in photographs of the Milky Way. The galaxy's disk has thick and thin components. The Milky Way's disk is actually composed of two overlapping structures, a thin disk containing young stars and active star formation, and a thicker disk populated by older stars with more elliptical orbits. This layered structure reflects the galaxy's evolutionary history, with the thick disk possibly formed during early mergers and the thin disk assembled more gradually over time. We live in the thin disk, surrounded by the galaxy's youngest stellar population. Stellar nurseries are hidden behind curtains of dust. Many of the galaxy's most active star-forming regions remain invisible to optical telescopes because they are shrouded in thick clouds of dust. These stellar nurseries reveal themselves only to infrared observations, which can penetrate the dusty veils to show the warm glow of newborn stars. Behind what appears to be empty darkness often lies the brilliant chaos of stellar birth, hidden from view but burning with the energy of cosmic creation. The galaxy breathes through a galactic fountain. Gas heated by supernovae and stellar winds rises from the Milky Way's disk into the halo, where it cools and eventually falls back down like rain in a process called the galactic fountain. This circulation helps regulate star formation and distributes heavy elements throughout the galaxy's structure. The Milky Way breathes slowly, inhaling and exhaling gas over millions of years in a rhythm too slow for human perception. Rogue planets drift alone between the stars. Not all planets orbit stars. Some wander freely through the galaxy as gravitational outcasts, either ejected from their birth systems or formed in isolation. These rogue worlds, dark and cold, may outnumber the planets that orbit stars, drifting invisibly through interstellar space. They are the galaxy's orphans, carrying no light of their own as they follow solitary paths through the cosmic wilderness. The Milky Way's center spins faster than its edges. Near the galactic core, stars complete their orbits in just a few million years, while stars in the outer regions like our Sun take hundreds of millions of years. This differential rotation would normally wind up the spiral arms until they disappeared, but density waves propagating through the disk maintain the spiral pattern by triggering star formation in organized sequences. The galaxy manages to preserve its elegant structure despite this internal shearing motion. Neutron stars serve as cosmic lighthouses, scattered throughout the galaxy, are the ultra-dense remnants of massive stars, neutron stars so compressed that a teaspoon of their material would weigh as much as a mountain. Some of these stellar corpses spin rapidly and emit beams of radiation, appearing as pulsars that flash with clockwork precision. These cosmic lighthouses help astronomers map the galaxy's structure and test fundamental physics in conditions impossible to replicate on Earth. The galaxy's age varies by location. Different parts of the Milky Way formed at different times, creating a complex archaeological record written in starlight. The central bulge and halo contain the galaxy's oldest stars, while the spiral arms host ongoing star formation. Reading the ages of stellar populations across the galaxy reveals how our cosmic home assembled itself over billions of years, growing from a collection of smaller structures into the grand spiral we see today. Magnetic fields accelerate particles to near light speed. The Milky Way's magnetic fields, though incredibly weak by earthly standards, can accelerate charged particles to energies approaching the speed of light. These cosmic rays, mostly protons and heavier atomic nuclei, bounce between magnetic field lines for millions of years before escaping the galaxy. They carry energy and information across vast distances, serving as messengers from the galaxy's most violent and energetic regions. The local bubble surrounds our solar system. Our Sun currently resides within a region called the local bubble, a cavity in the interstellar medium, roughly 1,000 light-years across, that was carved out by ancient supernova. This hot, tenuous region has much lower density than typical interstellar space, creating a kind of cosmic clearing in which we find ourselves. We live in a stellar suburb that was shaped by the violent deaths of massive stars millions of years ago. Tidal streams wrap around the galaxy like ribbons. When small galaxies are torn apart by the Milky Way's gravity, their stars form long, graceful streams that can wrap multiple times around our galaxy. These stellar ribbons, invisible to the naked eye but detectable through careful survey work, trace the orbital paths of their destroyed parent galaxies. They are among the most beautiful and delicate structures in the galaxy, like cosmic silk scarves draped across the darkness. The galaxy's rotation curve defies classical physics. According to Newton's laws, stars in the outer regions of the galaxy should orbit much more slowly than they actually do. The galaxy should not be able to hold itself together. This observation led to the discovery of dark matter, an invisible form of mass that provides the additional gravity needed to explain the galaxy's rotation. The Milky Way's motion reveals the presence of something we cannot see but cannot ignore. Star clusters slowly dissolve into the galactic field. Most stars are born in groups, but these stellar associations don't last forever. Over time, gravitational interactions and tidal forces from the galaxy gradually pull star clusters apart, dispersing their members into the general stellar population. Our Sun was likely born in such a cluster 4.6 billion years ago, and its siblings now drift somewhere among the galaxy's hundreds of billions of stars, forever lost to us. The Milky Way has invisible satellite galaxies. Some of the Milky Way's companion galaxies are so dominated by dark matter that they contain very few visible stars, making them nearly impossible to detect optically. These dark satellite galaxies reveal themselves only through their gravitational effects on nearby objects or through careful searches for their sparse stellar populations. They remind us that most of the universe's structure remains hidden from direct observation. Galactic archaeology reads the stellar fossil record. By studying the chemical composition and motions of stars throughout the galaxy, astronomers can reconstruct the Milky Way's formation history, like archaeologists piecing together ancient civilizations. Different stellar populations carry the chemical signatures of different epochs and environments, allowing us to identify which stars formed in the main galaxy and which originated in smaller systems that were later absorbed. The galaxy's bar drives spiral wave patterns. The central bar of stars acts like a cosmic stirring spoon, creating gravitational perturbations that propagate outward as spiral density waves. These waves compress gas and trigger star formation as they sweep through the disk, maintaining the galaxy's spiral pattern over billions of years. The bar is not just a feature of the galaxy's center, but an active driver of its overall structure and evolution. Interstellar space has different temperatures in different regions. The medium between stars is not uniformly cold, but exists in several phases with dramatically different temperatures. Cold molecular clouds hover just a few degrees above absolute zero, while hot bubbles carved by supernova can reach temperatures of millions of degrees. This multi-phase structure creates a complex ecosystem that regulates star formation and chemical evolution throughout the galaxy. The galaxy's chemical evolution continues today. Every generation of stars changes the chemical composition of the galaxy slightly, forging heavy elements in their cores and dispersing them through space when they die. This ongoing enrichment means that stars forming today have access to a richer palette of elements than their predecessors, enabling the formation of rocky planets and, potentially, life. The galaxy grows more chemically complex with each passing billion years. Stellar winds carve cavities in interstellar space. Massive stars don't wait until death to affect their surroundings throughout their lives. They blow powerful stellar winds that sweep up surrounding gas and dust into expanding bubbles. These stellar wind cavities can grow to hundreds of light years across, creating low-density regions where the next generation of stars may form. The galaxy's structure is constantly being reshaped by the breath of its most luminous residents. The Milky Way's mass is still uncertain. Despite being our home galaxy, astronomers still debate the Milky Way's total mass, with estimates ranging from 0.8 to 1.5 trillion times the mass of the Sun. Most of this uncertainty comes from the difficulty of measuring the extent and density of the dark matter halo that surrounds the visible galaxy. We know our cosmic address, but are still learning the basic specifications of our galactic neighborhood. Brown dwarfs are failed stars throughout the galaxy. Scattered throughout the Milky Way are objects that started to become stars but never accumulated enough mass to sustain nuclear fusion. These brown dwarfs, sometimes called failed stars, glow dimly with leftover heat from their formation and may be nearly as numerous as true stars. They represent the galaxy's incomplete attempts at stellar birth, glowing embers that never quite caught fire. The galaxy exhibits grand design spiral structure. Unlike galaxies with chaotic or fragmented spiral patterns, the Milky Way displays a grand design structure with two major spiral arms that can be traced for nearly complete circuits around the galactic center. This coherent pattern suggests that our galaxy has remained relatively undisturbed by major mergers for billions of years, allowing its elegant spiral architecture to develop and persist over cosmic time. Molecular clouds can remain stable for millions of years. Despite their gravitational tendency to collapse and form stars, many molecular clouds persist unchanged for millions of years before finally succumbing to star formation. Various forces, turbulence, magnetic fields, and stellar feedback can support these clouds against gravitational collapse, creating a delicate balance that determines when and where new stars will be born. The galaxy's stellar nurseries are patient, waiting for just the right conditions to give birth. The galactic center was once much more active. Evidence suggests that the Milky Way's central black hole was dramatically more active in the past, possibly shining as a brilliant quasar that could have been seen from other galaxies. Echoes of this ancient activity may still be visible in the form of high-energy structures extending from the galactic center. Our galaxy's heart once burned with the fury of accretion, but has since settled into a quieter old age. Stellar streams help map dark matter. The paths traced by stellar streams as they orbit the galaxy are sensitive to the distribution of dark matter, providing one of the best ways to map this invisible component. By observing how these streams bend and evolve over time, astronomers can infer the shape and density of the dark matter halo that dominates the galaxy's mass. Destroyed galaxies become tools for understanding the invisible architecture of our cosmic home. The galaxy's thick disk may record early violent history. The Milky Way's thick disk, populated by older stars with more chaotic orbits, may have formed during a period of intense mergers and interactions in the galaxy's youth. These stars preserve the signatures of ancient collisions that heated and stirred the early galactic disk, creating the puffed-up structure we observe today. The thick disk is a fossil record of the galaxy's turbulent adolescence. Cosmic ray acceleration happens at shock fronts. The galaxy's most energetic particles are accelerated at the shock fronts created by supernova explosions. where magnetic fields can boost particles to incredible energies over thousands of years. These cosmic particle accelerators operate throughout the galaxy, creating a population of high-energy messengers that carry information about the most violent stellar deaths. The galaxy generates its own particle physics laboratory in the aftermath of stellar catastrophes. The Milky Way's warp precesses like a spinning top. The galaxy's warp disk doesn't maintain a fixed orientation but slowly precesses or wobbles like a spinning top. This precession may be driven by the gravitational influence of the large and small Magellanic Clouds or by the torque exerted by the galaxy's dark matter halo. Even on galactic scales, nothing in the universe remains perfectly still or stable. Star formation efficiency is surprisingly low. Despite containing vast reservoirs of gas and dust, the Milky Way converts only about 1–3% of its available material into stars each billion years. Various processes, stellar feedback, turbulence, and magnetic fields, prevent rapid star formation and help regulate the galaxy's stellar birth rate. This inefficiency ensures that the galaxy will continue forming stars for many billions of years to come rather than exhausting its fuel supply quickly. The galaxy hosts exotic stellar remnants. Beyond ordinary stars, the Milky Way contains the compressed remains of stellar evolution white dwarfs, neutron stars, and black holes of various masses. These exotic objects, with densities and magnetic fields far beyond anything achievable on Earth, serve as natural laboratories for testing physics under extreme conditions. The galaxy's stellar graveyard teaches us about matter and energy in their most concentrated forms. Galactic chemical gradients trace star formation history. The abundance of heavy elements in stars varies systematically across the galaxy, generally decreasing with distance from the center. This chemical gradient reflects the galaxy's inside-out formation, with the central regions experiencing more intense star formation and chemical enrichment over cosmic time. The periodic table itself tells the story of how our galaxy assembled and evolved. Hypercompact stellar groups exist near the galactic center. In the extreme environment near the Milky Way's central black hole, stars can be packed so densely that they interact and merge on relatively short timescales. These hypercompact stellar groups, impossible in the galaxy's outer regions, create exotic stellar populations and may produce unusual types of stellar remnants. The galactic center operates by different rules than the suburban regions where we live. The galaxy's magnetic field may extend beyond its visible edge. Recent observations suggest that the Milky Way's magnetic field extends well beyond the visible stellar disk, possibly connecting with the magnetic fields of nearby galaxies in the local group. This extended magnetosphere could influence the galaxy's interactions with its environment and the flow of gas between galaxies. Even the spaces between galaxies may be threaded with invisible magnetic connections. Stellar kinematics reveal the galaxy's hidden structure. By measuring how stars move throughout the galaxy, astronomers can infer the presence of invisible mass concentrations and map the galaxy's gravitational field. This technique of stellar dynamics has revealed substructure within the galactic halo, evidence of past mergers, and the overall shape of the dark matter distribution. The motions of stars serve as tracers of the invisible forces that govern our galaxy. The Milky Way participates in cosmic web flows. Our galaxy is not isolated, but participates in the large-scale flows of matter through the cosmic web, the universe's grandest structure. Gas streams along dark matter filaments can feed the galaxy's continued growth, while gravitational interactions with the cosmic web influence the galaxy's motion through space. The Milky Way is both shaped by and helps to shape the universe's largest architectural elements. Ancient globular clusters may have formed outside the galaxy. Some of the Milky Way's globular clusters may have formed in other galaxies before being captured during ancient mergers. Their chemical compositions and orbital properties sometimes differ from what would be expected if they had always belonged to our galaxy. These immigrant stellar cities carry information about conditions in other galactic environments billions of years ago. The galaxy's spiral pattern is a long-lived wave. Despite the differential rotation that should wind up and destroy spiral arms, the Milky Way has maintained its grand spiral structure for billions of years. This persistence suggests that the spiral pattern is a long-lived density wave that propagates through the galactic disk like a permanent traffic jam, triggering star formation and maintaining its visibility across cosmic time. The galaxy's beauty lies in its ability to maintain order despite constant motion. Stellar multiplicity is common throughout the galaxy. Most stars in the Milky Way are not solitary like our Sun, but exist in binary or multiple star systems. These stellar partnerships can dramatically affect stellar evolution, leading to phenomena like Type Ia supernovae, X-ray binaries, and gravitational wave sources. The galaxy is filled not just with stars, but with gravitational relationships that bind stellar neighbors together across millions of years. The interstellar medium cycles between phases. Gas in the space between stars constantly cycles between cold molecular clouds, warm neutral regions, and hot ionized zones, driven by stellar feedback and supernova explosions. This multi-phase cycle regulates star formation and helps maintain the galaxy's ecological balance. The interstellar medium breathes with the rhythm of stellar birth and death, creating a dynamic environment for cosmic evolution. Dark matter subhalos orbit within the galactic halo. Computer simulations predict that hundreds of dark matter subhalos, the remnants of smaller structures that merged with the Milky Way, should still orbit within the galaxy's dark matter halo. Most of these subhalos are probably dark, containing little or no visible matter, making them extremely difficult to detect. Our galaxy may be surrounded by an invisible population of dark satellite structures. The galaxy's rotation has slowed over cosmic time. Like a spinning figure skater extending her arms, the Milky Way has gradually slowed its rotation as it has grown larger through accretion and mergers. This secular evolution affects the galaxy structure and the orbits of its stellar populations. The galaxy that exists today rotates more sedately than its younger, more compact predecessor of billions of years ago. Stellar archaeology reveals population mixing. The chemical compositions of stars in different parts of the galaxy show evidence of mixing processes that have redistributed stellar populations over billions of years. Radial migration, triggered by spiral density waves and gravitational perturbations, can move stars far from their birth locations. The galaxy's stellar populations have been stirred like cream in cosmic coffee, blending their original patterns into new configurations. The Milky Way's satellites show signs of disruption. Many of the small galaxies that orbit the Milky Way show evidence of being tidally disrupted by their larger companion. Stars are being stripped away, dark matter halos are being eroded, and some satellites are being gradually dissolved. This ongoing process of satellite destruction helps build up the galaxy's halo and provides insight into how large galaxies grow through hierarchical merging. Magneto-rotational instabilities affect galactic gas dynamics. Magnetic fields threading through the galaxy's gas can become unstable as the gas rotates, creating turbulent motions that affect star formation and chemical mixing. These magneto-rotational instabilities operate on scales from individual molecular clouds to the entire galactic disk, helping to transport angular momentum and regulate the galaxy's evolution. Even seemingly empty space participates in the galaxy's dynamic processes. The galaxy contains stellar streams from ongoing disruptions. Multiple stellar streams currently wrap around the Milky Way, created by satellite galaxies and globular clusters that are being torn apart by tidal forces. These streams evolve over time, becoming more dispersed and harder to detect as they age. The galaxy is actively dismantling some of its smaller companions, creating a fossil record of destruction written across the sky in streams of displaced stars. Cosmic ray pressure influences galactic structure. The pressure exerted by cosmic rays, high-energy particles accelerated by supernovae and other violent events, can be comparable to gas pressure in some parts of the galaxy. This cosmic ray pressure affects the dynamics of the interstellar medium and may help drive galactic winds that carry material into the halo. The galaxy's most energetic particles play an active role in shaping its structure and evolution. The Milky Way's central black hole is remarkably quiet. Compared to the supermassive black holes in many other galaxies, Sagittarius A is extraordinarily inactive, accreting material at a rate millions of times lower than its maximum possible consumption. This quiescence may be temporary on cosmic timescales. The central black hole could become much more active if a large gas cloud or disrupted star provides it with more fuel. Our galaxy's heart sleeps lightly, ready to wake if disturbed. Stellar feedback regulates galactic evolution. The energy and momentum injected into the interstellar medium by massive stars through stellar winds and supernova explosions helps regulate star formation and drive galactic-scale gas flows. This stellar feedback prevents the galaxy from converting its gas supply into stars too rapidly and helps maintain the complex, multi-phase structure of the interstellar medium. Stars actively participate in controlling their own birth rate and the galaxy's overall evolution. The galaxy's age-metallicity relation tells its chemical history. Older stars in the galaxy generally contain fewer heavy elements than younger stars, reflecting the gradual enrichment of the interstellar medium over cosmic time. However, this age-metallicity relation shows considerable scatter, indicating that chemical evolution has been a complex process involving mixing, infall, and perhaps variable star formation rates. The galaxy's chemical history is written in the stellar populations that surround us. Tidal forces from the galaxy affect satellite evolution. The gravitational field of the Milky Way doesn't just capture and destroy smaller galaxies, it also affects their internal structure and evolution. Tidal forces can trigger star formation in satellite galaxies, strip away their gas supplies, or alter their dark matter distributions. The galaxy's gravitational influence extends well beyond its visible boundaries, shaping the lives of its smaller companions across millions of light years. The galaxy participates in local group dynamics. The Milky Way's motion is influenced not just by its own internal structure, but by gravitational interactions with other members of the local group, particularly the Andromeda galaxy. These interactions affect the orbits of satellite galaxies and may influence the galaxy's overall evolution. Our galaxy exists not in isolation, but as part of a gravitationally bound system that will eventually merge into a single, larger structure. Stellar mass loss enriches the interstellar medium continuously. Throughout their lives, stars continuously lose mass through stellar winds, and this material enriches the surrounding interstellar medium with heavy elements forged in stellar cores. This ongoing process, separate from the dramatic dispersal that occurs during supernova explosions, provides a steady source of chemical enrichment that accumulates over billions of years. The galaxy grows more metal-rich through the gentle breathing of its stellar population. The galaxy's dark matter halo may contain fossil streams. Computer simulations suggest that the Milky Way's dark matter halo should contain numerous streams and substructures created by the disruption of dark matter subhalos over cosmic time. These purely dark matter streams, containing no visible stars, would be extremely difficult to detect, but could outnumber the stellar streams we observe. The invisible architecture of our galaxy may be far more complex than we currently recognize. Galactic chemical evolution varies with location. Different parts of the galaxy have experienced different rates and patterns of chemical enrichment, creating spatial variations in the abundance of heavy elements. The central regions, with their higher stellar densities and more active star formation histories, are generally more metal-rich than the outer disk and halo. The galaxy's chemical composition tells a story of uneven evolution across its vast structure. The Milky Way's bar may be growing stronger over time. Numerical simulations suggest that stellar bars like the one in the Milky Way tend to grow in strength over cosmic time, potentially affecting the galaxy's spiral structure and gas dynamics. A strengthening bar could alter the patterns of star formation and chemical evolution throughout the galactic disk. Our galaxy's central structure continues to evolve, potentially reshaping the entire system over billions of years. Stellar nurseries are regulated by feedback processes. The rate at which molecular clouds collapse to form stars is controlled by various feedback mechanisms, including radiation pressure from young stars, stellar winds, and supernova explosions. These processes prevent runaway star formation and help maintain the relatively low efficiency with which the galaxy converts gas into stars. The galaxy's stellar nurseries operate under strict regulation, ensuring sustainable star formation over cosmic time. The galaxy's gravitational field varies across its structure, different parts of the Milky Way experience different gravitational environments, affecting everything from stellar orbits to the stability of molecular clouds. The gravitational field is strongest near the center and weakest in the outer regions, but it's also shaped by non-axisymmetric features like the central bar and spiral arms. This varying gravitational landscape influences every aspect of the galaxy's structure and evolution. Cosmic ray propagation traces magnetic field structure. The paths that high-energy cosmic rays take through the galaxy are controlled by magnetic fields, and studying cosmic ray distributions can reveal information about the galaxy's magnetic structure. These energetic particles serve as probes of regions that are otherwise difficult to study, carrying information about magnetic field strengths and configurations from throughout the galactic disk and halo. The Milky Way's formation involved multiple phases. Rather than forming through a single, smooth collapse, the Milky Way assembled through multiple phases of accretion, merger, and internal evolution. Early rapid formation of the central bulge was followed by more gradual assembly of the disk and ongoing accretion of satellite galaxies. This complex formation history has left signatures in the galaxy's current structure and stellar populations. Stellar motions preserve memories of past events. The current velocities and positions of stars throughout the galaxy carry information about past gravitational disturbances, mergers, and other dynamical events. By studying stellar kinematics in detail, astronomers can work backward to reconstruct the galaxy's dynamical history, identifying when major mergers occurred and how they affected the galactic structure. Stars remember the gravitational shocks they have experienced over billions of years. The galaxy's spiral density waves trigger sequential star formation. As spiral density waves propagate through the galactic disk, they compress gas and trigger star formation in organized spatial and temporal sequences. This process can create chains of stellar associations and help maintain the galaxy's spiral structure over long periods. The galaxy's spiral pattern is not just a static feature, but an active driver of ongoing stellar birth and evolution. Galactic archaeology uses stellar abundance patterns. By measuring the detailed chemical compositions of individual stars, astronomers can identify which stars form together and trace the chemical evolution of different galactic components. Stars that formed from the same gas cloud or in the same environment carry similar chemical fingerprints, allowing researchers to reconstruct the galaxy's assembly history from the bottom up. Each star is a chemical fossil that records conditions in its birthplace billions of years ago. The Milky Way's mass assembly continues today. Although the galaxy formed billions of years ago, it continues to grow through the accretion of gas from the intergalactic medium and the ongoing disruption of satellite galaxies. This continuing mass assembly, though much slower than in the galaxy's youth, affects its current structure and will influence its future evolution. The Milky Way remains a work in progress, still adding to its mass and complexity. Magnetic reconnection events energize particles throughout the galaxy. When magnetic field lines in the interstellar medium reconnect and reconfigure, they can release stored magnetic energy and accelerate particles to high energies. These reconnection events, occurring throughout the galaxy's magnetized plasma, contribute to the population of cosmic rays and help maintain the galaxy's multi-temperature interstellar medium. The galaxy's magnetic field is not static but dynamically releases energy through reconnection processes. The galaxy's outer regions may extend much farther than previously thought. Recent observations have detected stellar streams and other structures at distances exceeding 300 Zarosan light-years from the galactic center, suggesting that the Milky Way's gravitational influence and structural components extend much farther into space than traditionally assumed. Our galaxy may be significantly larger than textbook descriptions suggest, with a more extended halo of dark matter and occasional stellar debris. Stellar feedback creates expanding superbubbles in the interstellar medium. When multiple massive stars in a stellar association explode as supernova over a relatively short period, their combined energy can create enormous cavities called superbubbles that can break out of the galactic disk entirely. These structures, hundreds of light years across, provide channels for hot gas to escape into the halo and help regulate the pressure of the interstellar medium. The galaxy breathes through these stellar-powered chimneys. The Milky Way's chemical evolution is still ongoing. Every new generation of stars continues to modify the galaxy's chemical composition, adding freshly synthesized heavy elements to the interstellar medium and gradually changing the raw materials available for planet formation. This chemical evolution proceeds at different rates in different parts of the galaxy, creating an ongoing transformation that will continue for billions of years. The galaxy's chemistry remains a dynamic, evolving system. Gravitational waves from stellar remnant mergers propagate throughout the galaxy. When compact stellar remnants like neutron stars and black holes spiral together and merge, they create ripples in spacetime called gravitational waves that propagate throughout the galaxy at the speed of light. These waves carry energy away from the merging systems and can be detected by sensitive instruments, opening a new window onto the galaxy's population of exotic stellar remnants and their violent interactions. The galaxy's future will be shaped by its collision with Andromeda. In approximately 4.5 billion years, the ongoing approach of the Andromeda galaxy will culminate in a major merger that will fundamentally reshape both galaxies. This collision will trigger new episodes of star formation, redistribute stellar populations, and eventually create a single, larger elliptical galaxy. The Milky Way's future is written in the slow gravitational dance with its nearest large neighbor. We are made from recycled stellar material. The final sleepy fact brings us home to ourselves. Every atom in your body except hydrogen was forged in the nuclear furnaces of stars and dispersed through the galaxy by stellar winds and supernova explosions. The calcium in your bones, the iron in your blood, and the oxygen you breathe all trace their origins to stellar processes that occurred billions of years ago in various parts of the galaxy. You are not just in the Milky Way is in you, a living embodiment of cosmic evolution and stellar alchemy. And now, as these 99 sleepy facts about our home galaxy begin to settle into your mind like stardust falling through cosmic night, let yourself drift deeper into the vast embrace of space and time. You have journeyed with me through billions of years and hundreds of thousands of light years, from the galaxy's ancient formation to its distant future merger with Andromeda. You've learned that you are floating through space at nearly 250,000 kilometers per hour, orbiting the galactic center in a cosmic dance that takes 250 million years to complete. You've discovered that most of the galaxy remains invisible, hidden in dark matter that outweighs everything we can see by 5 to 1. You've witnessed stellar nurseries giving birth to new suns, hypervelocity stars fleeing into intergalactic exile, and ancient stellar streams wrapped around our galaxy like ghostly ribbons from destroyed companions. The iron flowing through your veins was forged in the heart of a massive star that exploded billions of years ago, somewhere in the galaxy's vast spiral arms. The oxygen filling your lungs was created in stellar furnaces and scattered into space by stellar winds that took millions of years to cross the interstellar void. You are not separate from the Milky Way. You are a temporary gathering of its ancient stellar material, organized into consciousness and wonder, capable of contemplating the very cosmic processes that created you. Tonight, as you rest, the galaxy continues its patient rotation, carrying you and everything you've ever known on an endless journey through the universe. New stars are igniting in distant molecular clouds, their light-beginning journeys that may take millennia to reach Earth. Ancient stellar streams continue their graceful orbits, telling silent stories of galactic encounters from the distant past. Somewhere in the galaxy's vast halo, dark matter particles pass through each other in an invisible bullet that maintains the gravitational architecture, holding everything together. You are part of this cosmic story, not just an observer but a participant in the galaxy's ongoing evolution. Your thoughts, your dreams, even your peaceful breathing are part of the Milky Way's inventory of organized matter and energy. As you drift towards sleep, remember that you are floating within a structure so vast that light takes 100,000 years to cross it, so ancient that it has witnessed the birth and death of countless stellar generations, and so dynamic that it continues to grow and evolve with each passing million years. In the morning, when you wake, the galaxy will have carried you 20 million kilometers farther along its orbit around the cosmic web. the stars will have shifted imperceptibly in their slow gravitational dance, and somewhere in the galaxy's spiral arms, new stars will have begun their nuclear fires, adding their light to the vast river of starshine that illuminates our cosmic home. I hope these sleepy facts about the Milky Way have given your mind a peaceful place to wander as sleep finds you. Rest well in the knowledge that you are cradled within one of the universe's most beautiful and complex structures, a galaxy that is both your home and your heritage, written into your very atoms by billions of years of stellar evolution. Sweet dreams, fellow traveler of the Milky Way. May you sleep well and dream softly of spiral arms and stellar streams, of dark matter halos and galactic fountains, of the vast cosmic dance in which we all participate. Good night.